We are very close to our first lab, and boy, have we got a pile of labs to build a giant OSPF network. But before we do that, before we start configuring DRs and BDRs and spotting them and then wondering why there may not be a DR or BDR in a given segment, we need to know what the heck we're doing all this for to begin with. And it goes back to distance vector protocols and their, I'm putting it very kindly and censoring myself, their slow convergence. And convergence, of course, it's that state of nirvana for our network. Our network, every router's got a similar view of the network. It has an accurate view of the network. And that's particularly important, of course, right after a route goes down or a route is added. Because at one point, at the very beginning of that, only one router is going to know about it. And what we need is an efficient and, of course, fast way to get the news out to all the other routers about this network change, whether it be a route that's gone or a route that's been added. And you can hear the sigh coming into my voice already, because not only have I run into convergence issues with RIP, although it's been a while in a production network, boy, have I run into them in the lab. And I'm talking simple labs, nothing incredibly complicated. And you add a network and you've got just waiting for all the routers to multicast their updates and agree on the best route, that kind of thing. Because with RIP, it's not just routing loops we have to watch out for. And routing loops, of course, we're at layer 3, and that's when a packet goes into a logical circle trying to get from point A to point B. And a couple of routers just keep sending it back and forth. Could be 2 routers, could be 3, could be 4, but it just keeps going in a circle and it never gets anywhere until finally the packet just dies out. Well, the other issue we have with distance vector protocols is suboptimal routing. And this is where the packets are getting from point A to point B, but they're not getting there in the most efficient fashion, and that's what we're always looking for. So a couple of different issues with slow convergence there that we thankfully avoid when it comes to link state protocols, because link state protocols converge almost immediately, we got to say almost, upon a change in the network. Now, OSPF uses these DRs and BDRs, these designated routers and backup designated routers, to make this fast and orderly. And we like both of those because RIP, it just kind of throws it out there when there's a network change. It's like, hey, I'll just multicast or broadcast this out depending on which RIP version you're using, and just say, hey, hope somebody important gets it. But fast and orderly, we'll take that anytime we can get it. Here's what happens. Now, when a router on an OSPF segment that has both a DR and a BDR on it, when a router like that detects a change in the network, the detecting router does not notify all of its neighbors. It's not like RIP again, where you're just multicasting something out and hoping people get it. What happens here instead is that the detecting router sends a multicast to a different address than the hello address. Watch this one, 224.0.0.6. It's the all designated routers address, and the DR and the BDR on that segment will hear it. DR others do not listen for 224.0.0.6. So that's only an address for DRs and BDRs. They both hear it, and this is what happens. So these other two routers that would be on the same segment, they would not know about it yet because the router detecting it is going to send that change to 224.0.0.6. The DR will then multicast to 224.0.0.5, our hello packet address or hello address. And this is officially the all OSPF routers address. That's why we send hellos to 224.0.0.5, because this is a multicast address that all OSPF routers listen to, every single one. So if only the DR sends that multicast out, the musical question, although I won't sing it, is why does the BDR get it so fast? Well, the thing is, we always want the BDR to be able to step into the virtual shoes of the DR at any moment if that DR goes down. And by doing it this way, the BDR gets the update the same time the DR does. It updates its own OSPF database, and it's ready to go in case the DR goes down. But again, only the DR sends that particular multicast to 224.0.0.5. And that's it. That's how orderly that change is. Now we're going to look at the DR BDR election process here. We saw a little bit of that in a debug, but we want to know exactly what's going on and why this value called the OSPF router ID or the RID, why it matters. And we're going to look at the rules and regulations about these elections. We'll see them all live on several different network types, several different segment types. And if you're on a broadcast segment, then one router is going to become the DR, another will become the BDR. And if you had four routers on that segment, the other two would become DR others, which is a fancy way of saying a router that is neither the DR nor the BDR. If you had 7 routers on there, then you'd have 5 DR others. That's what's going to happen with the broadcast segment. And you might see a little bit of something like this, where you would be asked, who's going to be the DR here? Who's going to be the BDR here? What are the OSPF router IDs? So you might want to write this one down. I'll show it to you again shortly without the switch. But again, we've got routers 1 and 2. They both have loopbacks. Routers 3 and 4 don't. So, the RID choice may be a little limited there on 3 and 4. But let's take a look at these rules. Very important stuff here. Every router interface on the segment with an OSPF interface priority of 1 or greater, they're all eligible to participate in the election. The priority default is 1. So by default, everybody's going to be in on the election. And setting the interface priority to 0 is a way to disqualify that router from participating in the election. I have a feeling we might see some of that here shortly. Now, simple enough, the router with the highest interface priority is elected DR. And of course that makes you think, well, if they're all set to the default of 1, and what happens then when there's a tie? Because there's probably going to be a tie unless we change the priority. Actually, there will be a tie unless you change the priority. What happens then? The RID is the tiebreaker, and the router with the highest RID is going to win. So that's why we need to know how the heck OSPF comes up with router IDs, because the same process is going to be repeated to elect a new BDR. And by the way, a single router can't be the DR and the BDR for the same segment. And just to reinforce that, every segment in our network is treated separately when it comes to the DR and BDR. We are not going to have one designated router for one ginormous OSPF deployment. Every segment on there, whether it be broadcast or NBMA or point-to-point, is going to have its own DR BDR election. Again, that's all coming up live, but I just want to make sure that I stress that we don't just have one DR in the middle of a big OSPF deployment. What we do need to know now, though, is exactly how the router comes up with that RID. Now, it can be hard-coded. It can be hard-coded with the router ID command, but by default, the RID of any given router, any OSPF speaking router, is going to be the highest IP address that's assigned to a loopback interface on that router, regardless of whether that loopback is actually OSPF enabled. And I say that with emphasis and with italics because it's such an important rule. And you got to admit it's a little odd, right? Because your first thought when you see it is, well, an interface would have to be OSPF enabled for its IP address to be used as the RID. Well, no, it doesn't. And if that doesn't come up on your exam somehow, I would be shocked. Now, of course, the next question is, what if there is no loopback? Rare is the production router that you're going to run into that does not have a loopback interface on there. And they are used for all different kinds of purposes. Not many that you see in the CCNA curriculum, unfortunately, because that's probably the #1 question I get after people take the course and they pass the exam and they say, hey, what about these loopbacks? Do we ever use those for anything? And we do. And this is one place where the loopbacks come into play is with the OSPF RID. But if you're on a router that doesn't have one, then the OSPF RID will be the highest IP address assigned to a physical interface. And again, that interface does not have to be OSPF enabled in order for its IP address to serve as the RID. So a really important fact to keep in mind. It'll be easy points for you on the exam. You just got to keep that in mind. Now, we'll wrap this up though. We'll go through here, these 4 routers we were looking at, and determine what the RID of each one will be, determine what the DR would be for this segment, assuming they're all on the same segment, and which one would be the BDR. I took the switch out of this one just to make it a little clearer, but you see the addresses there, and on a couple of them, routers 3 and 4, the RID choice is pretty simple, right? Because there's no loopback and there's only one interface with an IP address. So router 4's RID would be 172.114, router 3's would be 172.113. Routers 1 and 2, the loopbacks would be, the RIDs would be 1111 and 2222 respectively, and the question wouldn't even have to say which interfaces are OSPF enabled, because we know an interface doesn't have to be OSPF enabled in order to have its address used as the RID. And yes, that is the last time I'll say that for now. But I know something else, you're thinking at the same time when you're looking at this, it's like, well, what if there are no IP addresses? Well, actually, what would happen in that case, if you try to run OSPF on a router and you don't have an IP address on any interface that's open and up and running, then it's just going to tell you point blank, hey, can't do that. Can't even start OSPF. It's a little scary when you first see the message. It's like, is my router broken? Your router is not broken. The message actually says something along the lines of, hey, you know, we can't get a RID. So that's the first thing OSPF does when you enable on a router. It's got to come up with that OSPF RID, and if you don't have an address, it can't get a RID, and it's going to say, hey, you know, good night. You know, fix that, and then I'll come back and do something for you. We do have some more theory to cover, but I think you've had enough of that for right now. What we're going to do is go ahead and start with the labs. Coming up next, we'll build a broadcast segment, an NBMA segment. We're going to see all kinds of OSPF little gotchas and details and show commands, maybe a debug or two as well. And that is all starting next.